start by reviewing the theory of operation of a synchronous AC generator presented earlier in this course prior to our discussion of generator protection. When current flows through a conductor, a magnetic field is formed. The higher the current flow, the stronger the magnetic field. An electromagnet can be formed by winding the conductor around a material such as iron, which has a low permeability or resistance to the flow of magnetic lines of flux. Depending on the direction of current flow, one end of the iron core will be a north pole, while the other is a south pole. The magnetic lines of flux will leave the north pole and flow to the south pole, returning to the north pole through the iron core. When magnetic lines of flux cut through a conductor, a voltage is induced in the conductor. The magnitude of the voltage is proportional to both the strength of the magnetic field and the speed with which the magnetic field cuts through the conductor. A single-phase generator is composed of two major components, the exciter and the stator. The exciter is an electromagnet that rotates about its axis as shown. The stator is constructed from two electromagnets or poles wired in series to a load and, as the name implies, remains stationary. As the exciter rotates, its magnetic field cuts through the windings of the stator poles, inducing a voltage and hence current, which will flow through the attached load as shown. Large utility-class generators produce three-phase alternating current, and so our single-phase generator is modified with the addition of two more pole pairs. The poles would be positioned such that the pole pairs are directly opposite each other, and planes running through any two pairs of poles will intersect at an angle of 120 degrees. This arrangement of poles forms the stator of a two-pole, three-phase generator. It is called a two-pole generator because the stator has two electromagnetic poles per phase. One side of each pair of windings is connected together, while the other side is connected to our three-phase load. If we plot a graph of the voltage which appears across each of our load resistors against time as the exciter rotates through one revolution, we will see the waveforms shown. As the exciter rotates, the voltage induced in each pair of stator windings will be displaced by 120 electrical degrees from the other two waveforms, corresponding to the physical angular position of the stator windings. The resulting output is the desired three sine waves of equal amplitude, but with a 120-degree phase shift between them as shown. There are many sources of generation for electrical power: hydroelectric, nuclear, natural gas, and fossil fuels, just to mention a few. The mechanical systems used to convert these sources of energy into electrical power vary greatly in both physical construction and in mechanical limitations. For example, a hydraulic turbine is designed to withstand overspeeds that occur during startup and shutdown, while on the other hand, a steam turbine with base speeds in the 3200 RPM range will sustain damage during an overspeed condition even if for only a few seconds. From a protective relaying perspective, these vastly differing generating systems translate into a challenging problem. The operation of protective elements will generate a trip when protecting one style of generator, while on another, the element may either not be enabled, or if enabled, may only generate an alarm. In addition to the mechanical arrangement, a typical generator system consists of a synchronization unit, an automatic voltage regulator, speed regulator, and a protective relay. Let's begin by looking at the synchronization unit. It's very important that within a power system, the power being generated matches the power being demanded by the network. The synchronization unit ensures that the frequency and phase angle of the generated power matches that of the rest of the network. It does this by sending a feedback signal to a primary generator speed regulator. For example, the gas valve controller of a natural gas generator, which will increase or decrease the speed of the generator. This increase and decrease is used to sync the generator's output frequency to the network. Once the generator is in sync, the synchronization circuits will provide an in-sync signal output. The automatic voltage regulator is also an essential component in matching the power being generated to the power demanded by the network. The AVR ensures that the generator's voltage magnitude matches that of the network. It does this by summing the negative feedback from the generator's output voltage with that of the network. The error signal is fed to the generator field current regulator. This increases or decreases the field strength so that the generator voltage magnitude matches that of the network. The last of these three components is a protective relay. A relay will be connected to the generator stator circuit and will provide generator stator protection in addition to backup protection for the AVR and the governor. In addition to these components, the correct selection of current transformers for the protective relay is an essential part of proper generator protection. The current transformers should be matched and a fault study conducted to determine the maximum CT primary fault current. With this information, the CTs chosen should be such that maximum voltage at the CT secondary terminals at the time of the fault is less than 50% of the CT knee voltage. Further information on CTs in general, along with specific CT selection principles, can be found within the Power Systems section of this CD. Grounding strategies are a very important part of ensuring proper generator protection. Generators alone are very expensive. When coupled with the cost of unscheduled downtime for a repair, total losses in production can be very high. The most costly and time-consuming repair is metal damage. That is, damage to the steel laminations forming the stator and rotor of a generator. It's been found that if the fault current is above 10 amps, metal damage can occur. It's important for a grounding strategy to ensure that the fault current remains at or below 10 amps, and therefore damage will be minimal. The grounding strategy employed is the key factor determining the magnitude of the fault current. Let's look at an example of a generator ground fault. Within this large generator, a fault occurs due to insulation deterioration. A high level of fault current will then go to ground following the path of least resistance. With no grounding strategy in place, the full amount of fault current will flow back into the generator. If this cycle were allowed to continue, the damage to the generator would be quite extensive. The general purpose of a grounding strategy is to decrease the level of fault current that is allowed to flow back into the generator during a ground fault condition. We will now examine some of the common grounding strategies used to protect generators. The first strategy we will look at is the high impedance grounding scheme, of which there are two types. The first is high resistance, and the second is ground fault neutralizer. The high resistance scheme uses a grounding transformer and a resistor connected across the secondary. With large generators, a distribution transformer is used as a grounding transformer. Let's look at a ground fault within a generator using the high resistance scheme. As fault current flows to ground, the transformer will drastically reduce the level of fault current. Therefore, the amount of fault current flowing back into the generator is also greatly reduced. This means that the damage that could occur to the generator during a ground fault will be far less. Generally, high impedance schemes limit the primary current to between 3 to 25 amps. The second type of high impedance grounding is ground fault neutralizer grounding, also known as a Peterson coil. This type of grounding uses reactance instead of resistance on the secondary. The advantage of reactance is that it can be adjusted to limit the ground fault current to different levels. The Peterson coil is capable of limiting the fault current to 1 amp. The second strategy we will discuss is low-resistance generator grounding. In this strategy, generators have their neutral grounded through a resistance such that typical fault currents are in the range of 200 amps up to 150% of rated full load current. The resistor required for low-resistance grounding can be quite expensive and large. Therefore, this grounding strategy is usually not employed with smaller generators. This type of grounding is used where 2 or more generators are bused at generator voltage and connected to a system through one step-up transformer. This type of grounding is also used where the generator is connected directly to a distribution system having a low-impedance grounding source on the generator bus. The third strategy is reactance grounding. This method uses an inductive reactance between the generator neutral and ground. With this type of grounding, the phase-to-ground fault current will range from approximately 25 to 100% of three-phase current. This grounding method is usually used where the generator is directly connected to a solidly grounded distribution system. The fourth strategy is direct grounded or zero-impedance generator grounding. Generators that use zero-impedance grounding have extremely high fault currents which are very easy to detect. At the time of fault, there is a lot of fault energy, and so the reaction time to the fault has to be very fast to limit damage. The final strategy we'll discuss is non-grounded generators. This type of grounding is popular in marine applications and in some areas of Europe. At the time of a ground fault, there is no fault current flow, and so the reaction time can be slow. Detection is difficult due to the lack of current. Voltage elements such as neutral displacement are typically used to detect such faults. In this section, we will discuss the most common protective elements used within generator protection schemes. Protective elements are essential in providing proper protection for all components within a power system, including generators. The elements we will cover fall into one of three categories: primary generator protective elements, backup elements for the AVR, or backup elements for the governor. The first primary generator protective element we will discuss is the phase differential element, which consists of the well-known dual slope percent restraint characteristic. Let's quickly review its operation. The phase differential element operates by utilizing the differential signal and the restraint signal. 3 differential elements are used, one for each of the generator's windings. For each, a differential signal is derived from the phasor sum of the current flowing into and out of each phase of the generator's stator windings, I1 and I2 respectively. Let's assume for the moment that our CTs are ideal, that is, having no error. Therefore, the CTs on both sides of the generator measure 200 amps. If the CT secondary currents are viewed on a phasor diagram, we will see the currents will sum to 0, resulting in a differential of 0. There are many accepted ways of calculating the restraint signal. In our example, we will use the average of I1 and I2. When we plot the results on the dual slope percent restraint characteristic curve, we see that the resultant is well below the operating region. The slopes of the element can be adjusted to accommodate CT error and saturation to create a characteristic that is sensitive enough to detect faults at low current levels, while achieving security for high through-fault current conditions with additional CT error due to saturation. For further detail on the percent differential element, please refer to the differential element description under the Distribution tab. The second primary generator protective element we will discuss is 100% stator ground fault protection, which can be achieved using a combination of fundamental frequency neutral overvoltage and third harmonic neutral undervoltage. A standard fundamental frequency neutral overvoltage protection element can provide ground fault protection for 95% of the generator stator winding. In case of ground faults in the final 5% of the winding, there will be such a low fault current or such a small imbalance in voltage that conventional protection cannot reliably detect it. On a healthy three-phase power system, there is no or very little neutral voltage since all 3 phases are at 120 degrees to one another. However, once a ground fault occurs, this balance is upset and a neutral voltage is produced. The neutral overvoltage function responds to fundamental frequency voltage at the generator neutral. It provides ground fault protection for approximately 95% of the stator windings. Normally, there are 2 stages of operation, since it is common that the system has been designed to withstand an overvoltage condition for a certain period of time following a ground fault. In such applications, an alarm is generated as soon as the fault is detected. This gives time for the system operators to locate and isolate the fault. The second stage of operation will issue a trip command if the fault condition persists. To detect faults in the last 5% of the generator winding, the third harmonic neutral undervoltage element is used. The neutral undervoltage element senses the collapse of the third harmonic voltage between neutral and ground when a fault close to the generator's neutral occurs. The third harmonic undervoltage element also has, in most cases, 2 stages of operation, one for alarm and another for trip. The ground directional element is used on small generators that are solidly grounded and paralleled to determine which generator has the ground fault. A relay will detect ground directional by using zero sequence voltage and zero sequence current, which are represented as V0 and I0. The angle between these quantities determines if a ground fault is within the generator or not. This function should be coordinated with 95% stator ground protection to ensure that this element operates faster. This is to ensure that a faulty generator will be tripped before other protection elements trip the healthy generators operating in parallel. This element must use a core balanced CT to derive the I0 signal. Polarity is critical in this element. The protection element is blocked for low neutral voltages. If the ground directional element is enabled, the neutral overvoltage element should be coordinated with it. In cases of parallel generator grounds through the same point with individual ground switches, it is recommended to use a ground switch status function to prevent maloperation of the element. Negative sequence overcurrent is also a primary generator protective element. Negative sequence currents are produced during system unbalance conditions such as faults or load unbalances, the most serious unbalance condition being an open phase. Rotor heating in generators due to negative sequence current is a well-known phenomenon. Generators have very specific capability limits where unbalanced current is concerned. You can refer to the ANSI C50.13 document for details. A generator should have a rating for both continuous and also short-time operation when negative sequence current components are present. The manufacturer of a generator assigns a constant known as K to the generator depending on its size and design. The K constant represents the short-time negative sequence capability of that generator. K is proportional to the thermal capacity of the generator rotor. Modern generator protection relays, such as the GE Multilin SR489, have a definite time alarm and inverse time overcurrent curve trip to protect the generator rotor from overheating due to the presence of negative sequence currents. The pickup values are in units of negative sequence current as a percent of generator-rated full load current. The generator FLA is calculated as generator-rated MVA divided by square root 3 times rated generator phase-to-phase voltage. Negative sequence overcurrent maximum time defines the maximum time that any value of negative sequence current in excess of the pickup value will be allowed to persist before a trip is issued. The reset rate provides a thermal memory of previous unbalance conditions. It is the linear reset time from the threshold of trip. Generators are normally able to withstand a certain level of negative sequence stator current continuously. The generator manufacturer will provide a continuous maximum negative sequence phase sequence rating. It is important to note that unusually high negative sequence current levels may be caused by incorrect phase CT wiring. Low forward power protection is the next primary generator protective element we will discuss. While the governor should control overspeeding, for some generators, low forward power protection may be required to protect the prime mover in overspeed conditions. Under normal conditions, there is a balance between the generated power and the load. When the load is removed, this balance is interrupted and the generator will start to speed up. This can lead to the prime mover accelerating to unsafe speeds. This is known as overspeeding. In some cases, low forward power protection is used as an interlocking function to enable opening of the main circuit breaker for non-urgent trips such as stator ground faults on a high-impedance grounded generator, or to prevent the generator from going into a reverse power condition. This is to ensure that the generator circuit breaker is opened only when the output power is sufficiently low that overspeeding is unlikely. For urgent trip situations, such as stator differential protection trip operation, the prime mover and generator breaker must be tripped simultaneously. The low forward power element is blocked while the generator is offline, and will remain blocked until the generator has successfully been connected to the power system. The pickup level is set below the minimum forward power that can be expected during normal operation. For example, if the minimum power that is being consumed by the system is 20 megawatts, then the low forward power setting should be set lower than 20 megawatts. The next primary generator protective element we will discuss is reverse power protection. Under normal conditions, a generator is expected to supply power to the connected system. Let's look at an example where the generator prime mover fails, that is, the source of mechanical energy fails. This generator, which is connected in parallel with another source of electrical supply, will begin to draw power from that source instead of supplying power. This phenomenon is also called motoring of a generator. This reversal of power flow due to the loss of the prime mover can be detected by reverse power protection. This element is used to prevent damage to mechanical parts of the plant in the event of failure of the prime mover or loss of mechanical power. The reverse power protection element is also used to trip the generator to prevent turbine blade heating and other adverse effects in turbo generators. The time delay settings for reverse power protection should be set to avoid spurious tripping with transient power swings that may arise following synchronization or in the event of power transmission system disturbances. Inadvertent energization is the final primary generator protective element we will discuss. If the generator is inadvertently brought online without being up to speed and synchronized, or is at standstill when the breaker is closed, severe damage could occur. The generator will act as an induction motor if the circuit breaker is closed when the generator is at standstill. Very high currents would be induced in the rotor and stator components, resulting in rapid overheating and damage. The inadvertent energization protective element may be armed when all of the phase voltages fall below the under-voltage pickup level and the unit is offline. This would be the case when the VTs are on the generator side of the disconnect device. If, however, the VTs are on the power system side of the disconnect device, the feature should be armed if all of the phase voltages fall below the under-voltage pickup level or the unit is offline. When the feature is armed, if any one of the phase currents measured at the output CTs exceeds the overcurrent level programmed, a trip will occur. The next three elements we will discuss are the backup elements for the AVR. The first element is the loss of excitation protective element. If the generator is initially operating at only 20 to 30% of rated power, and with loss of excitation, it might be able to run for several minutes before it has to be tripped. There might be sufficient time for remedial action to restore the excitation. If loss of excitation occurs when the generator is operating at high power output, the rotor speed may rise to approximately 105% of the rated speed. In such a situation, it would draw a high reactive current from the power system. In this case, a rapid automatic trip is required to protect the stator windings and rotor. The next backup element for the AVR is the overvoltage protection element. Overvoltages on a generator may occur due to transient surges on the network or a variety of other conditions. A sustained overvoltage condition should not occur for a machine with a healthy voltage regulator. There are situations where the voltage regulator might not function correctly, such as the automatic voltage regulator being defective, the generator operating under manual control with the AVR out of service, or there is a sudden loss of load such as the tripping of outgoing feeders. For these reasons, it is critical to provide power frequency overvoltage protection. The final backup element for the AVR we will discuss is the overfluxing protective element. Overfluxing occurs when the ratio of voltage to frequency is too high. The iron saturates due to high flux density and results in stray flux occurring in components that are not designed to carry it. Overheating can then occur that will result in damages. Either excessive voltage or low frequency, or a combination of both, can result in overfluxing. Overfluxing affects both directly and indirectly connected generators. The first backup element for the governor we will discuss is underfrequency protection. Underfrequency occurs as a result of the overloading of generators operating on an isolated system, or due to a serious fault on the power system that results in a deficit of generation power to load. As an example, a grid system suffers a major fault on transmission lines linking the two parts of the system, and the system then splits into two. It is possible that one part will have an excess of generation power, and the other will have a corresponding deficit. Underfrequency conditions will occur in the latter part. Generally speaking, an underfrequency condition on a generator will occur when the power system load exceeds the prime mover capability of a generator or group of generators. Load shedding schemes will try to remedy the situation. If load shedding fails, then the generator has to be tripped by underfrequency protection. Operation of generators at lower frequency with nominal voltage should be limited as much as possible to avoid damage to the generator and associated equipment. The second backup element for the governor is overfrequency protection. An overfrequency condition occurs when the mechanical power input to the prime mover is in excess of electrical load. We can see in our example that the section of the system with an excess of power is in an overfrequency condition. This can occur if the governor does not respond quickly to reduce the mechanical input power. Moderate overfrequency operation of a generator is not as potentially dangerous as underfrequency. Normally, actions can be taken at the generating plant to remedy the situation without shutting down the generator. However, severe overfrequency operation of a high-speed generator could be dangerous and damaging to the generating unit and associated equipment. Let's look at an example of a breaker failure protective element. In this example, the protective relays operate correctly, but the associated circuit breaker fails to clear the fault because of some malfunction within the breaker or its control circuits. The fault will now remain on the system until some other means is used to clear it. In our example, the primary or backup relays start a timer once a fault has been detected. The timer will then time out and send a trip signal to all breakers that can feed the failed breaker with power.